Good evening, everyone. I'm going to present my research on mixed cell height legalization. What sets my work apart is that it's the first to address the vertical abutment constraint in legalization. Here is the outline. In the introduction, I will start by introducing the vertical abutment constraint and discussing relevant prior research. We will then define the problem we aim to solve. The second section will provide a concise overview of our proposed method. Finally, we will delve into the experimental results in the last section. The vertical abutment constraint in our works serves to model both existing and forthcoming interval constraint. For each benchmark, we choose a specific cell type as the vertical abutted constraint cell. In the graph below, the red cell represents the vertical abutted constraint cell. Our proposed constraint prohibits any cell from being placed at the 8th relative position indicated in the graph. NIA and NOL are two interval constraints that previously work primarily considered. The distinction between NIA's constraint and the vertical abutment constraint we address lies in the fact that NIA only requires that the overlapping width of certain cells exceeds a certain requirement when they vertically abut. In contrast, constraints imposed by NOL are more akin to those we tackle. Due to patterning limitation, NOL restricts certain cells from vertically abutting at a specific position. In the final slide of the introduction, we define the problem that our algorithm aims to solve. Given the results of global placement and the following hard constraints, the goal of the algorithm is to minimize both the average cell displacement and maximum cell displacement. So next, I'm going to introduce the proposed algorithm. Our algorithm follows a sequential approach, which means legalizing cells one by one. However, we have adopted a different order compared with conventional methods. Specifically, we prioritize sorting cells based on their height first and then on their width as the secondary sorting criterion. The reason behind this order is that the algorithm is allowed to adjust the positions of previously legalized cells when legalizing a new cell. However, we aim to minimize modification to the previous placement as much as possible. Placing taller cells often requires moving more cells to create space. Therefore, we prioritize placing taller cells first, ensuring that in the later stage of legalization, only the shorter cells need to be processed. This approach helps to minimize significant change to the previous placement. In this slide, I'm going to introduce the flow of our sequential legalizer. At the beginning, cells with the same height are sorted in descending order based on their width, with the widest cell being placed first. Next, in the purple box, we will sequentially examine each cell to determine if it can be directly placed on the nearest site to its global position without causing any violations. If the cell can be placed without any issues, it will position at that location. If not, the cell will be added to a queue. Once the condition of each cell has been confirmed, the purple box here will handle the cells that were pushed into the queue. The general process of legalization for a cell in the queue first finds candidate position for placing the cell. Then, based on the cost function, the best position is selected for the cell to be placed. A detailed explanation of this process will be introduced in the later slides. In this example, we will demonstrate how to find candidate position for the target cell, which is the cell being legalized. The blue color cell is the target cell. The black dashed rectangle is the closest site to its global position. The remaining cells are already legalized. It's evident that the target cell cannot be directly placed on its nearest site because it will overlap with the cell on its right, and it will also cause an edge spacing violation with the cell on its left. According to the description in the paper, the algorithm can identify these dashed red angles as candidate positions. Therefore, the next step is to determine which candidate is the most suitable one to place the target cell. The subroutine choose-based site finds the best candidate to place the target cell according to the cost function. Here is a brief summary of its operation. It first attempts to place the target cell at a candidate position. If this placement results in any violations, the algorithm moves other cells to resolve these violations. Once all violations are addressed through cell movement, a set of cost functions is used to evaluate the impact of step 1 and 2 on the overall placement. During the process of placing the target cell and moving other cells, 3 types of violation may occur, which are overlap, edge spacing violation, and vertical abutment violation. After attempting to place the target cell on each candidate position, the algorithm ultimately selects the candidate site with the lowest cost to place the target cell. In this example, we will illustrate how to move previously legalized cell to resolve overlap and edge spacing violation. The blue T cell represents the cell currently undergoing legalization. When attempting to place it in the shown position, it overlaps with cell A and C. To resolve the overlap and edge spacing violation, we spread neighboring cells to the left and right with the minimum shift required to solve all design rule violations. Here is an example of a vertical abutment violation. As you can see, when we place the blue target cell at the site, it kills a vertical abutment violation between cell T and E. Once more, we employ the spreading method to resolve vertical abutment violations. Let me reiterate the legalization flow for a cell that cannot be directly placed at the site closest to its global position. First, the algorithm collects candidate sites for the cell to be placed. Next, it attempts to place the cell on each candidate site while spreading neighboring cells to resolve all violations. Each candidate site thus has a cost that represents how much placing the cell at the candidate affects the overall placement quality. Finally, the algorithm chooses the candidate site with the lowest cost to place the cell. The benchmark used in this study are sourced from the 2017 ICCAT contest, which is a common benchmark employed by nearly all recent studies on mixed cell high legalization. The tables provide an overview of these benchmarks. The second column represents the number of single high cells, while the third, fourth, and the fifth column represent the number of double high, triple high, and quadruple high cells respectively. The last column indicates the design density of these benchmarks. We conducted 2 experiments. The first, and to evaluate the effectiveness of our algorithm when considering only conventional legalization constraint without the vertical abutment constraint. In the second experiment, we sought to confirm our algorithm's ability to handle the vertical abutment constraint. Here are the results of the first experiment. The first place represents the winner in the ICCAT contest, while the reference 3 is a paper published at 2022 ISPD, which is currently one of the best mixed cell high legalization algorithms. In the table, both forms indicate the best result of each metric. Our algorithm achieved the lowest average displacement across nearly all designs. There are only 4 cases where we did not achieve the best result, but the differences are very small. Regarding the comparison of maximum displacement, asterisks denote optimal solutions. The reason why we can confirm they are optimal will be explained in the next slide. Our algorithm finds 7 optimal solutions among the 16 designs, resulting in the lowest average maximum displacement. In terms of runtime comparison, as we don't have access to the code of the other 2 approaches, the data is directly obtained from their papers. Objectively, they use better hardware, and our runtime only lags behind the third reference. On average, our algorithm takes around 2 seconds to legalize a design, which we consider fully acceptable. This slide explains why we can confirm that certain designs achieve an optimal maximum displacement. In these designs, there are fixed macros where some cells are placed within the area occupied by land during global placement. There is the shortest distance to move this cell out of the fixed macro area. If this distance is the maximum displacement in this design, we can confirm that this is the optimal maximum displacement for the design. The second experiment aims to validate our algorithm's ability to handle the vertical boundary constraint. The without VAC column represents the performance of our algorithm without considering the vertical boundary constraint, essentially the outcome from the previous experiment. The with VAC column represent our algorithm's performance after considering the vertical boundary constraint. In the number of VAV column, the value is the number of vertical boundary violations when not considering the vertical boundary constraint. After incorporating the vertical boundary constraint, our algorithm generates solution without any violations. Under this condition, our algorithm only requires an additional 2% overhead average displacement on average to handle all vertical boundary violations. The performance in terms of maximum displacement remains almost the same. While there is more variance in the runtime, we think it is still acceptable considering that our vertical boundary constraint has 8 relative positions that need to be checked for a cell. So this is my presentation. Thanks for your listening.